Hello, everyone. Okay, all of you, welcome today. It's a little bit different today, uh, in the sense that I'm actually recording it about half a day earlier than the previous episodes because many of our scientists are away. Uh, the group of scientific forum that we have. Uh, my group is away, and then so I also have some appointment tomorrow, so I had to record this earlier so that we can continue the scheduled meetings. So, in the spirit of doing that, I thought that I will record it, not only like half an hour to 1 hour today, just the presentation, and then hopefully next week or subsequent week we'll have all our scientific group coming back, and then we'll have a detailed discussion about on this topic as well as other topics. So, without much ado, let me briefly mention that these episodes we are carrying out are the history of physics, and essentially we have now the four episodes. The three episodes already passed. Episode one, we talked about the what led to the classical physics, and that was well received. There were many viewers, and then we have episode two, which is the more specific aspects of thermodynamics and Maxwell equations. So we are following along the history path, and then the next century, which is closer to our century, we had this only beginning of actually 19th century to 20th century, that really the structure of the atom was fully revealed, and that kind of justified Maxwell's understanding of the electric and magnetic field. As we know, Maxwell developed that based on Faraday and Ampere as well as Gauss. They found the electric and magnetic fields. When they measured it, they found these forces, and they described, and Maxwell fully described altogether the mathematics of that, the four equations that we know, but they were combined from Faraday's law and Gauss's law as well as the Ampere's law, put them together, and he found a special uh, circuit current that was necessary to complete the equation. So the mathematics became very, very important, as we know, as we discussed in the last episodes. And then Rutherford actually found the structure of the atom that we described in episode three. Uh, Originally, Dalton mentioned about atom is the most indivisible one, but when Thomson started measuring the electrons, and there's particles that can be accelerated through screens, uh, especially cathode ray tube, then the subsequently Rutherford used alpha ray, and then he found that there is a very heavy uh, entity within the atom. So the whole structure of the atom then was had to be revised. So now we have, you know, neutrons and electrons and positrons. So essentially, positrons and the neutrons occupying the nucleus. It is a very highly dense uh, state of the middle of the atom. And then you have a lot of empty space, and then electrons are orbiting it. And then you have various orbits that can starts forming. So many scientists, including Bohr, started developing uh, techniques to find out the orbits, how the electrons move, and they started measuring that. And as we know, that these required the problem, you know, they solved the problem of the structure of the atom, but they started new problem. This is what we are going to discuss today. Why, how the quantum mechanics, theory of relativity, and space-time then started and changed the whole sphere of classical physics. So this is now we are transitioning actually historically from the 16th to 17th century. We started classical physics, and that was developing. And we knew that the most important aspect was the conservation law that Maxwell, along with Carnot and other people, developed uh, the laws of thermodynamics. The first law says energy cannot be destroyed or created, but so the energy conservation became very strong and the fundamental aspect all of mathematical physics. Now, we will actually discuss that. Like I mentioned previous episodes, we plan to have Hawaiian conference as well as a World University eventually. But in the auditorium, we plan to have a separate discussion starting philosophical aspects. Uh, hopefully detailed audio discussions that describes about the conservation law as the holy grail of physics. And even now, like we mentioned again in the previous episodes, that the momentum conservation was a challenge. It could not be, you know, shown. The momentum, then we have to move into angular momentum, consideration angular momentum, and the field that Maxwell eventually said. So the idea is that even if the original energy or the force may not be or the momentum cannot be conserved, how about the differential of that? Will it be conserved? So this is how the field theory came into being, and even now that's a challenge with standard model, like I mentioned, and we continue exploring this aspect. This is one of the reasons we are going back to the blackboard that we will mention after this episode start becoming clearer that why we had to do these episodes because there are a lot of some confusion started occurring and some inconsistencies and problem with physics started and the matching between the experimental and the theoretical aspects and also the mathematics started developing by its own almost detaching from physics like the string theory but then we'll see that these are not necessarily that we can totally discard. They do form pieces of the puzzle. So that's what we are developing, and as we move on, we are just resetting to the classical physics, and we are just advancing in algorithmic way the minimal understanding we need to have. So there won't be much mathematics we'll consider, neither we'll consider, too much detailed physics, but basic physics and so that everybody can follow along in schools or colleges. So this is the idea. So like I say previously in for my presentation, we can use these aspects and then we are going to hopefully have once we finish all the episodes to have uh, a text production of a movie that will detail for everybody, like Oppenheimer, uh, a brief understanding of what physics overall is and why that was necessary. So, without much ado, let me move on to our topic for today. It's a historical significance of quantum mechanics. We start with quantum mechanics, and then let me mention quantum mechanics, and then um, theory of relativity started becoming contemporary physics. So now, actually, we are, from classical physics to uh, quantum relativity to contemporary physics to modern physics. We are transitioning almost because, as we see here, the emergence of the old quantum theories started developing as part of the modern physics. So quantum mechanics started developing as modern physics. Emergence of quantum mechanics to explain the phenomena, and this was a problem for the classical physics that quantum has to take it up. The black body radiation. How do you explain that? Photoelectric effect. which talks about the particle nature. Until then, the light was thought to be in the Newtonian physics and other aspects as wave theory. The wave theory of the light was prominent, but Newton did, mention about corpuscular theory. We'll have more discussions later on about these aspects, but mainly the solar emission spectra. So the continuum aspects was not really observed in many other experimental aspects. So that has to be explained. The old quantum theories laid the foundation groundwork for quantum mechanics. So one of the persons, I mentioned about Bohr last time, and we will come back to it. But in this particular episode, we will have to concentrate on Max Planck and back Brownian radiation because that was a very important step. 1900. Now we are already in this in the last century. Uh, Max Planck introduced the concept of quanta to explain back body radiation. So, in order to explain the back body radiation, he was trying to fit the data from low temperature, high temperature, and then uh, how the black body radiation occurs, things like that. So, he worked intensely, and its work demonstrated that energy is quantized, can take only specific values. So, it doesn't, if you input energy, it doesn't immediately come, do the emission or if there is a uh, you know there is a absorption or emission, they don't occur a continuous fashion. So the there is something is happening inside that is trying to get to a certain level of energy before it can either release or absorb. So this aspect is where the quanta aspects started coming into picture. Albert Einstein did contribute to the photoelectric effect. As we know, he was not favoring quantum mechanics per se in the particular aspect that we'll discuss in the next episodes and further down. But Einstein himself, 1905, was discovered the photoelectric effect, and he got a Nobel Prize for that. And he showed light to be as particles. You call it photons and waves. Uh, he did work closely with Planck and all other scientists, Bohr, as we know, and he was trying to explain the corresponding with the energy and frequency. Uh, Crucial step towards quantum mechanics. So Einstein did contribute some aspects about the fact that there could be a frequency dependence, but it was Max Planck who really did the complete math, a simple math, as we know, E equal to h nu that he came up with, uh, h being the Planck constant. That became the fundamental cornerstone for quantum physics. The wave mechanics and Erwin Schrödinger, and then came Schrödinger, and in 1925, a little bit later, uh, so we are coming closer to the 20th century here. Erwin Schrödinger developed mathematically wave mechanics that describes how particles like electrons exhibit both wave-like and particle-like behavior. We'll examine in more detail about Schrödinger equation, but essentially it said that the electrons itself can exhibit wave-like and particle-like behavior. So do the light. So this became the very important aspect of the quantum mechanics. As we know, it changed the whole aspect of physics itself. So the modern era, quantum field theory with practical application. So quantum mechanics prompted a philosophical upheaval in understanding of science. The phrase quantum mechanics was coined by physicists including Max Born, Werner Heisenberg, as we see the Heisenberg uncertainty principle. We won't spend too much time in this episode, but we'll later on look into uh, Heisenberg, where he talked about the fact that the measurement aspects that you cannot accurately measure both position and momentum at the same time. Um, and then Wolfgang Pauli, who talked about Pauli exclusion principle, that no two electrons have the same type of spin. The spin aspects also became very important. That you can say quantum mechanics in a way was instrumental in inventing that aspect of the spin itself, the early 1920s. So these became again back part of the physics research in the atomic and subatomic processes. Now, after Rutherford, atomic physics started looking more into detail, especially subatomic particles. And as we know, the spectrum of particles start increasing. Practical applications included transistors were developed because of these. As we know, we are not going to detail about transistors, but charge movement, migration, and things like that. The charges of the particles became important, especially electrons, and you can minority carriers and majority carriers, and semiconductors and conductors and insulators. They became key in developing transistors and all the chips later on. Initially, uh, it was not a solid state chips initially, but it became. Now all the computers are solid state chips. Um, so the cathode ray tube essentially was even replaced by all these uh, transistors and semiconductors and all the microprocessor chips. Then it heard the development of lasers, because lasers again is light amplified stimulated emitted radiation, which means you have the quantum aspects where you have the sodium vapor lamp, you split into two wavelengths. Again, I'm going to go into detail, but that aspect said that you can concentrate on one particular wavelength aspect, and also the wave function and everything started coming into picture, and they developed fantastic devices using lasers, and we use them a lot because highly concentrated and coherent lights. Uh, a lot more discussions will come about coherence and other aspects later on. As we know from Rutherford and then from Einstein, special relativity, the nuclear reactors came because we know that they were highly dense batteries concentrated at the center of the atom. And we have a way to really harness this enormous power. And briefly, let me mention that the neutrons and neutron, so the alpha ray, which is a sensor, if you send a neutron and you bombard with a neutron, it can release a neutron from the atom, such as a very heavy atom like uranium. So it is all logged in. It's all what you call caged in, like in a cage, and you release that. That energy is Einstein proved that from previous work of others, from the equivalence principle with the energy in mass that E equal to mc squared. So these create enormous energy, the stored energy that became part of the nuclear reactions. And as we know, atom bomb or peaceful nuclear reactors, by using proper control roads, it's used everywhere now as it's prolific energy generators. Uh, so now we go into relativity, the hot topic, right? The historical significance of theory of relativity. So special theory of relativity. So by those times, so these things happen hand by hand for quantum mechanics and the theory of relativity. So in Albert Einstein He proposed the special relativity in 1905. As you know, that he initially find the photoelectric effect, but he started going into the special relativity. And part of the reason is because of the measurement of speed of light. And you see, he was motivated by Maxwell equations, which said there should be vacuum and there should be, aether. So that question of vacuum and aether became a very important topic for Einstein, and how the light, uh, the behavior of light, small distance, large distances, and of course the correspondence principle, the conservation and things like that came into being. And we'll be talking more and more as we go on. And it's an active area of research for us also. It's ongoing research. So this special relativity changed the whole understanding of space, time, and motion. So initially, everything was understood by the Newtonian mechanics, space and time, absolute time, and the space and all that, and instantaneity of light, things like that. Uh, for Einstein, the law of physics changed. Uh, he said that it should be same. He started looking at the observers and how the light travels, how the behavior light. And there's so much of detail that even now it's very hard to comprehend for most of the people. And there are questions as to why, as to the whether it's falsifiable, things like that. We are looking into that. So, if it is a non-accelerating initial motion, which is non-accelerating frame, like in vacuum, then it should be the same for observers. Uh, so the physics, laws of the physics. So it's a very deep aspect of the physics that Einstein covered. That we need, there are a lot of lectures, like I mentioned. This is just the gist of it, and there are a lot of courses on theory, relativity, books, and everything that you know, and then videos and our own research that we are to looking more into that to understand the details of it. Here we are just mainly giving the gist of it. The speed of light in a vacuum is constant. This was the main aspect of Einstein, that for observers, regardless of their relative motion, this became the cornerstone to establish uh, the relativity and extending to astrophysics and beyond. Uh, we'll see uh, samples of that here. So the consequences of the all I'm going to mention is the consequences, and the details are enormous because there are a lot of math involved. And I'm going to give a brief preview of the math, especially of the general relativity, but uh, essentially used Lorentzian transform. So the transforms became a very important part of understanding of the reference frames, the space, time, how they mix together, uh, and and then as we see the space and time, Minkowski said it's all connected together, and we'll see more about that. The consequences of special relativity, and it is sometimes confusing. So we want to use these episodes to sort out what was actually happening at that time, and only to that degree. So we'll be restricting to that, so that understanding is that much we understand it clearly. That's what I want to ensure that. So the time dilation, what exactly is that? Moving clocks run slower relative to stationary ones, significant at high speeds. So the moving clocks, that is, if it's in motion, right, uh, they run slower. Okay, that's time dilation. So because of that's the effect of the momentum. So the actual momentum, because they are all relative uh, from Lorentzian transform. So the time itself is relative to the movement, essentially. Length contraction. Objects appear shorter along their direction of motion relative to speed. So this happens close to the speed of light. It doesn't happen the normal mesoscopic level that we are way below the speed of light. So the velocity is way below. The speed is way below the speed of light. All the Newtonian physics applies perfectly, right? Only when we reach the speed of light, when you are at that speed, like particles do, electrons and the particles do. So it matters there. Uh, and then if you are talking about, in any objects, even astro objects, which are of that kind, then you have to take into account, according to Einstein theory of relativity, special theory of relativity, uh, length contraction. So you are time dilation, length contraction. Then you have mass and energy equivalent. Einstein's famous equation equal to mc square relates mass and energy, like I mentioned before. But m in this case is called relativistic mass. Again, I'm going. It's not the Newtonian mass, but corrected for the speed of light. Uh, so that is something that it's m naught or rest mass versus speed of light. So m naught over square root of one minus v squared by c squared. So that is the mass and energy equivalence. The bending of light, that even Newton observed that, but Einstein could predict actually massive objects can bend light due to gravitational effects, and that was proved in the 1919 solar eclipse as well. So he uh, calculate exactly how much it will bend because of these uh, gravity, because of the gravitational effect. So that was what made Einstein's theory stick to a large degree. Later found groundwork for understanding Big Bang and origin of our universe. So later on, of course, Hubble and other scientists started looking into how the objects move, the astro objects move, and the very larger modeling of the whole universal phenomena that led to understanding that, backtracking and then understanding that the origin of the universe might have occurred by a big bang. Again, these are all little bit of controversial topics even now, and there are a lot of uh, experiments that have confirmed that, but also that has questioned, that continuously questioning especially new James Webb telescope measurements does question some of the aspects, and that requires more advancement and modification, things like that. But in general, the special theory seems to be uh, explaining a lot of the phenomena. Then Einstein said that okay, uh, special theory applies to that, but doesn't consider about the gravity special theory. So he had to come up with a general theory. So he was planning to come up with a unification. At that time, that now the forces are not just electromagnetic, not just gravitation, but also weak nuclear and strong nuclear. Strong nuclear is where the nucleus of the atom is involved, like in nuclear physics, right? It's very, very short range. But the weak nuclei is where most of the electrons are participating. The nucleus is not participating, but the electrons are participating, especially in chemical reactions, things like that. So, and then van der Waals forces, things like that. So these became part of the weak nuclei, and also uh, I should mention that the main aspect is the radioactive measurements, right? So the radioactivity which releases is part of the uh, weak theories. So there are a lot more details, and one has to aspect that when you talk about strong nuclear fields, strong nuclear forces, which means we are we are releasing the enormous energy E equal to mc squared then. Okay, whereas the in the weak nuclear cases, We are just electrons and their alpha particles and all other muons and other aspects are involved. Uh, so that's a very simple, a distinction that we can make to keep in mind. But there are a lot more details in that we'll explore some of it as we go along. But there is enormous amount of literature that we have to go through to understand them completely. And then a lot of scientists in the world, even now, developing many aspects, including our own group, uh, how the paradigm changes with that. But they have become very important part of the thing. And I should mention that I have critically examined these to myself along with my scientists, and I believe that they are important. These concepts are important, but they may need lot of modifications. The key principles in the general relativity is the equivalence principle is one of them. The equivalence principle says the gravitational acceleration is indistributive acceleration due to other forces. This Einstein has proved by elevator experiments and other experiments, thought experiments even, and also it was conducted later on that he just the acceleration and the gravity are essentially the same, but they have the difference that is described by general relativity equation that we'll be going over. But that's the important principle that's sometimes very hard to understand. A lot of videos, and then like Sabina or something, they have described these uh, simple experiments to understand. Curvature of space-time. Massive objects were the space-time fabric uh, affecting motion of the object. This was the key thing for coming up with general theory of relativity equation, form the fundamental basis of understanding all of the star system, and then with the Schwarzschild metric solutions, the idea of black holes, wormholes, and other aspects that can warp the space-time because. So there are regions which are enormous amount of gravity, and that changes the space-time. As we see later on, the main departure from the classical physics, Newtonian physics, is that gravity is not a force, gravity is not the fundamental force, but the warping of the space-time or the bending of the space-time and the changing the shape of the space-time from the flat, which is essentially like a vacuum, to curved space is the reason why you have masses. And this is done by mass of the object does this job. Excuse me. Consequences. Gravitational time dilation. So the consequences of that generally brings about is that clocks near massive objects run slower, like in black holes, things like that, where you have very high level of gravity. Uh, they do time dilation is very large. Uh, Predicted black holes. Massive collapsed stars create regions of extreme space-time curvature. So this is a very important aspect. Uh, so the collapsed stars create regions of extreme space-time curvature. So if you have black holes, they warp the space-time. They create large amount of space-time curvature that changes the whole physics around them. Wormholes, they're the hypothetical shortcuts through space-time. So wormholes connect the space-time with black holes, uh, and then they also connect black holes and then white holes and all that. So this bridge, we'll talk about Einstein producing Rosenstein's bridge, is one such wormhole. That also came from Schwarzschild metric. He was one of the first ones to solve Einstein equations. So those are consequences of that. Cosmic expansion. Theory of the relativity supports idea of expanding universe. So that connected with Hubble's uh, measurements and also Hubble's model that the whole universe is expanding continuously from that because of the Big Bang. So the whole universe starts with the Big Bang. That's the bottom line of the model. So some of the experiments confirm these aspects, like precise mention of bending of starlight during a solar eclipse in 1919 is, Eddington and other people measured that very accurately, and that laid the foundation and then kind of proved uh, the viability of general theory of relativity to explain all of the phenomena in the universe to some degree, to a large degree. And our understanding of the universe improved, and then some predictability aspects also came into possible aspects. Of course, it transformed understanding of the cosmos, challenged the classical notions of absolute time and space, and they remain foundational in modern physics and continue to inspire scientific exploration. So now let's look back into quantum mechanics. So I'll be switching between quantum mechanics and relativity, as I said. They are contemporary physics, and there are a lot of interaction between. So I just want to give extra a flavor for the historical developments. They are overlapping, each other, and I want to present that. It's not a sequential thing. A lot of it. So there is sort of interaction because the quantum mechanics used E equal to mc square to some degree, Einstein thing, and first, and Einstein tried to understand or trying to modify question some of the quantum mechanical aspects as well. Uh, so Minkowski space describes space-time the absence of gravitation. So Minkowski was one of the teachers, Einstein's teachers. He developed the math, and he was quite interested in Einstein's development of the relativity. And he said that you can combine inertial space, which is space where there's no supposed gravitation, like vacuum, and time manifolds to four-dimensional model. So space and time can be uh, quantified together, and that was Minkowski. Minkowski space-time is defined by Lorentzian metric tensor. I'm not going to detail about the math. Some of the math are highly involved, but we are going to understand qualitatively mostly, but with some quantification, sufficient quantification to get you know a proper understanding without confusion. That's what I'm trying to get at here. So Lorentzian metric tensor, and we'll go a little bit into what metric tensor, things like that. But in subsequent episodes, we'll try to dissect these aspects because and then dilute it to some degree so that I can get a better understanding of what it is, right? And then once we understand, then we go into detail and how to work it out. That's what we are hoping in the subsequent episodes to, to actually delineate the complexity or the complicatedness into more simpler, uh, you know, versions of that. A framework. So the Lorentzian metric is a framework understanding geometry of space-time. So geometry is involved to describe the geometry, the tensor. You have a metric tensor that describes the geometry. And the later on, of course, we'll show that we need space group, the group theory and things like that to actually see that, to ensure the geometry, we have described the geometry correctly. Uh, in a way, it's a kind of a conservation law that is applied in this case, but it's not same as the energy conservation that the dynamics has done. So that's still a challenge. Uh, Time in quantum mechanics has a distinct role in space, and that's very, very important. And then this is one thing I have looked into, and I already have published a paper that actually the time is not uh, just a simple scalar quantity; it is a tensor. So that has not been developed during that time, but that's the area I am developing further, and I'm showing that that could explain some of the gaps, something that we don't understand otherwise. But in any case, that's much later presentations. Matter and energy are intertwined in space-time. As we know from equivalence principle, energy and mass are integrated. Space-time group is a continuous flow of a space-time. So these concepts are important. What is a space-time group? It's a continuous flow of space-time, representing matter and interaction field. So as we know, the matter and energy are intertwined. So the question arises whether everything is a field, that you can think of a mass as a condensed field and a wave as expanded field, right? In general. And these are things we are considering even further. Minkowski isometries forming a 10-dimensional non-abelian Lie group is Poincare group. The Poincare group, so we are trying to see the patterns, right? And then we compare the patterns, and the patterns are repeating in certain way. We can understand the properties. We can classify the properties and understand the properties altogether. As a bulk, as a group. Uh, so this is the main idea of finding the patterns and then the symmetry groups, so that we can do uh, transformations, conservative transformation. So this understanding of how the patterns group has led to understanding isometries, uh, Lie group, which has specific pattern repetitions, and also high level of symmetry properties, symmetric properties. And then you have to talk about dimensions. So Poincare group then talks about more about space time. Uh, Laurentian group more about the space aspect, but Poincare group extends to the space time itself. The unified space time symmetries, including translations. So now, what happens when they get translated or moves rotations? Translation is a linear movement, but mostly rotations. Then you have rotations. Then you have many rotations possible, right? Theta, phi, gamma, which is all rotations uh, in different planes, x, y, z, and if you talk about even a Euclidean geometry, x, y, z, the rotations, they have three different types of rotations. Again, I'm going to detail about that, and that's a study by itself. We are looking into that, and some aspects will be discussed in later episodes. The boosts, again, what the boosts are, connecting space-time, particles, and solidity. So when you talk about the particles, how they interact, what the symmetries involved in there, how they affect the space-time, how they translate through the space, travel through the space-time, how they change that, how the space-time changes particles, perhaps particles change the space-time, these kinds of things. Uh, and then we we see the relativity automatically comes to picture, right? The smaller scales, the Planck scale, space-time may be a kind of quantum form. So this is the general. Now Planck scale is a smaller scale that can exist, uh, below which there is no real particles. They are partonians or partons or quasi particles, but they are not real matter. So you need a minimum Planck scale to have a real matter particle. But the quantum form aspects, is also restricted, as we see that Christopher Brothers manual. We are looking into that, but the question of quantum form has been a problem, cannot describe black holes or wormholes. So we have to restrict the understanding of quantum form, and the gravity is not part of that. This is what I'm also developing. That if we consider gravity separately and the electromagnetism, then we can talk about quantum form, and that will show how it is conserved, how there's a universal network that the light can travel through. So we have to describe the universality of light and perhaps of the electrons as well. And quantum form may be the best way to describe. We will go into details more about that. Now, let's look into some mathematics and nothing other than the Schrodinger equation itself, which forms the crux of the quantum mechanics, the quantification. So it talks about quaternions here in this case. So this is a big departure. Now we are talking about imaginary things, the complex variables. So not just uh, represents. So because it considers both fields and particles. Particles have mass, fields have their frequency or wavelength. It's combining both. So how does Schrodinger do that? So I'm not going to derive that again. Uh, there are a lot of I will present a reference in the next pages uh, of how the Schrodinger details of the quantum mechanics one and two. There are videos that completely describe the derivation as well as the formation of that. So the I in this case is square root of -1, and h is the reduced Planck constant 1 over psi t. Now we have to be very careful. This is a part of the wave function, the time component of the wave function, and then we describe the variation of this wave function uh, with respect to time, and then that is equated to the variation. As we'll see that the wave function contains both space and time, but you can separate uh, wave function, these that I will show in the subsequent page, that you can separate them into the time form and the space form, and uh, and then you can describe uh, the space form separately uh, of the wave function, and that uh, is again h squared, which is again Planck constant over 2m. So the space constant in this case talks about the mass aspect or the particle aspect. Here it talks about more about the wave aspect. And that del square phi x, which is the space component of the wave function, over that's a second derivative of the space. So as we see that uh, that is then the kinetic energy, and then you have the potential energy. This is what makes the Schrodinger equation so complicated. The psi t itself, the time component of the wave function, is an evolution. Time evolution has been proved to be time evolution exponential function given here. And then, so we can describe this uh, the whole aspect of the the space component, uh, the whole space component in terms of the energy times the wave function. So this is the actual wave function, which should include both space and time. So then that is equal to phi of x, which is the space component, times the evolution component. So this is how you solve the time independence Schrodinger equation. And the important aspect here is the Hamiltonian operator. The Hamiltonian operator is described by this h square over 2m del square over del x square operator for a kinetic energy operator. And then you have potential energy. So you see that the operator mathematics get started becoming open. So everything is now described in terms of operators instead of just objects, motion, or equation of motion, things like that. So that's a big departure that started happening in the physics. So the Hamiltonian of a wave function, which is an operator. So Hamiltonian operates uh, on the space component of the wave function, and that is equal to the energy times the space component of the wave function. So the Hamiltonian essentially describes the energy aspect. The, uh, it contains the total energy. So it's actually a total energy. Hamiltonian is the total energy operator using Schrodinger wave equation. So it contains both kinetic energy as well as potential energy. But it's an operator, right? So you have to multiply, you have to operate on the wave function to produce the results. That's equivalent to total energy. So this is where you have to wrap your head around that to figure that out. And we'll go into more and more details to really dissect that and simplify that as much as possible. But you have to understand the way it is, and most of it is taken that essentially the wave function is the whole key to the quantum mechanics that we described. That's all I want to say right now, uh, because there are so many details about it. Okay. Now, let's go back into theory of relativity. So these are very, very mind-bending aspects, right? Now people are combined both quantum mechanics and theory of relativity. One of the reasons I am going switching back and forth between the two, because we have to understand them in a holistic way. So space-time is a mathematical model that combines three-dimensional space, length, width, height, and then in normal geometry you talk about length, width, and height. But uh, in space-time, you have to add the dimension of time. They are all combined together in a single four-dimensional continuum. General relativity space-time is a four-dimensional manifold, the Lorentzian metric tensor defined on it. So this is how you describe that. So you have a big departure from Euclidean geometry, right? Manifold represents the combined fabric of space and time, where massive objects warp this geometry. Like you see, very simple picture here. So you have a space-time and you have an object here, and that's warping the space-time. So if this object is not there, this ball is not here, the fabric will be very flat, right? It will be simple planar aspect, simple plane. But this one now is dipping that, right? Now we are not talking about gravity. Normally we think, oh, okay, there's a gravity pulling. No, that's not what it is here. It's that that object here somehow dilates all the fabric around it, just in the vicinity of it, or curves it. It's a simple name for its curving it. And this is described by the Lorentzian metric tensor. Manifold represents the combined fabric. Okay. The space-time curvature explains gravity and phenomena like black holes. So based on that, Einstein could with the shape of the geometry, Einstein could describe gravity. He was trying to combine that, he was trying to unify that. But there were problems with that. Okay, we'll see later on. But of course, this was solved by Schwarzschild metric, and that's how the black hole aspects came to be. Einstein himself didn't predict that based on his theory. That's very important to know. So, what are Lorentzian transformations? The equation relate measurements made by observers moving relate to each other. So, when two objects are moving relate to each other, uh, the time and space coordinates change, right, continuously. So, spatially you are moving, but at the same time, the clock is running. Clock is not stopping. So that's what it's trying to capture. So the transform you need transformation to keep track of both of them together. Einstein extended his theory to include gravity, resulting in general relativity. Key ideas of Einstein relativity space-time is that one of them is the curved space-time. Mass and energy distort space-time. As we see, the mass here is distorting the space-time. Massive objects create curves affecting motion of other objects. This is he generalized that for all of the universal star systems and planets and all that. And many other measurements does confirm his thing, but there are questions that's coming up that needs more, you know, in-depth modifications. Equivalence principle. Gravitation is equivalent to acceleration. Because falling freely in a gravitational field feels like being in a zero gravity. That's very, very important. So, how is that equivalence principle coming into picture, right? So, that's very, very important. So, here described by many cases how if you are in that, if you are not aware that you're nothing, you will think that you are falling freely, right? Uh, Gravitational field as if you are in zero gravity. So it's a connection with the environment, relationship that makes us feel that the gravity is acting in that way. It's different from the acceleration, but it is not really. So locally equivalent to acceleration. So it's a localized phenomenon. Actually, gravity is a local. This is what I'm looking into more, and I'm able to discover, for example, tortuosity, things like that. I come as factor and how developing the whole idea of time tensor and the gravity gradient, things like acting together with certain properties to create what I call coupling and interaction to create gravity effect. So this is what I'm looking into. My research quantification, and you may be able to solve that problem, but it requires a lot more research, to group theory and other aspects to really understand how we can put them together. The Einstein's field equation. So this is the famous Einstein field equation. I will go into a little more detail about that. They describe how mass and energy determine the curvature of space-time. Okay, so let's go into the detail of the Einstein equation. Einstein simplified in a very compact form the whole idea of the universe in this form. Uh, the energy and the mass, gravity, and all the fields and everything together here. It includes everything. This, it's a tensor. If you expand it, you can write this tensor out. That's a huge. It takes a lot of space by itself. So G mu nu in this case is an Einstein space-time curvature tensor. It describes how the how the objects curve the space, how the geometry is changed because of that. So that is a big factor here. Then you have lambda, capital lambda G mu nu, which is the curvature space-time cosmological constant times the uh, G mu nu is symmetric tensor, is a tensor. Then I have not separated it out. Actually, lambda is a curvature. And then we'll go into the details about the equation in the subsequent thing. Uh, in this case, the c is speed of light, g is the gravitation constant. It's called the Einstein gravitation constant. So they are different from Newtonian gravitation constant. Uh, so curvature and two different things. Okay, here you should read that way. And T mu nu is a stress energy tensor, which talks about the local energy, momentum, and stress. So it combines all of that. And we'll see what are the components of this stress energy tensor. So in this compact equation, a lot of things involved. And we'll expand some of the aspects in the next subsequent slide. But there are a lot more involved. So gravitation waves. So from this, people are looking into that. These derivations take, many lessons and also description, right? In a advanced physics course. So they are highly involved. But they predicted gravitation wave ripples in space-time caused by accident because of this stress energy tensor and everything. So that these things should create ripples in space. And this has been proved now. The Lego experiment, the Lego experiment for which people got Nobel Prize recently, they proved the gravitation waves indeed is true. And these are created by black holes, things like that in space time and travels through space. Here, the information of what's going on there. Mass and energy are interchangeable. E equal to mc square, massive objects crowd space time affecting the motion of others. So, example is the black hole itself. So they affect everything and whatever, as we know, they say event horizon, things like that. We are going to go into detail, but the objects fall into the region of the black hole or event horizon. And once they pass that, they cannot return. So even the light cannot escape. Of course, later on we know that in the you know uh, Hawking radiation, things like that. So one of the persons who study in detail is Stephen Hawking himself about these aspects using the general theory of relativity and all his associates and all, there's so millions of papers, millions of researchers who have done since Einstein uh, about the relativity, much like the quantum mechanics itself. They do form the two main branches of physics these days. And very important to note that American theoretical physicist John Wheeler talked about Einstein's theory of relativity, and his quote, let me quote, and that's a very famous quote, gives the overall picture of what it is. Matter tells space-time how to curve, and curve space-time tells matter how to move. You see that? So that's a very, very important aspect. So this object here uh, tells how it should curve geometrically, right? And the curved space-time then tells, okay, now it's my turn to tell you how you can move further. You curved me, now I'll tell you how you can move further because now you are caught in there. Now this is the curvature is going to determine the equation of motion, right? So this is the complex aspect of the mass and the space-time. It's kind of like entanglement in a way, right? So the quantum mechanics come into picture automatically. So quantum relativity, quantum gravity come into picture. Or in any case, that's a later talk. The black holes are regions of extreme space-time curvature where nothing, not even light, can escape. That's a very important aspect. So solutions of Schrodinger. Now we are switching back to Schrodinger. Like I said, we are switching back and because they are contemporary physics and quantum relativity is a very intertwined aspect. So historically, even that's why I want to bring it up. So solution Schrodinger equation. separating variable, time and space. So this is a crux of the thing. I'm just putting the main points only. Without that, you cannot solve Schrodinger equation. And we'll see for relativity, general relativity, without the Schwarzschild metric, there were no real solutions. Okay. When dealing with a system that depends on both position and time, we can separate the wave function into two parts. Substitute separated wave function into the Schrodinger equation to get time evolution equation and time independent equation of the wave function. So this is actually the wave function. When you talk about wave function, like a psi, it should have both space and time. In this case, it's a one-dimensional aspect. For example, x and t. Only then it's a wave function. If it's just psi x is just a component. It's very important to remember. This is a one-dimensional space we are taking, for example. In one dimension, time independent Schrodinger is given by. So we write in one dimension, try to solve it, and then you can generalize later on. But to understand how the solution works, we need one-dimensional model. So that's del x squared, right? Del x squared plus psi xt, where m is the mass of the particle, h bar is the reduced Planck constant, v of xt is potential energy, right? Uh, Function of space and time. This is the complete equation. Okay. Psi is a wave function, psi x of t. Now, separation of variable, let psi of xt, psi of x times psi of t. This has been proved. As we know the references, the two references, time dependent Schrodinger equation, and you should watch uh, this video by Brian Carlson, who is a professor in a university, talks about quantum mechanics 1 and 2 different courses. I especially in this particular video talked about separation variable Schrodinger equation. Why? How mathematically it is correct to do this aspect. So this has been proved that you can actually separate the space and time separately, and that's mathematically provable. To be independent of time, in this case, when you talk about the potential, it doesn't change with time. So specific cases of potential energy has to be considered to solve the problem. We cannot generalize potential energy. So you have to like a quantum well, or or you have a situation, particle in a box, things like that. You have very specific geometry and very specific uh, potential energy uh, cases. So then you can solve for each of the cases how the wave equation comes into the wave function uh, gets solved. So we can describe wave function that way. Of course, uh, finally, quantum mechanics believe that the whole universe is described by one wave function. So that we are not going to go into detail why that is so, but you can watch many of these Sabine Hasselfield or recently Sam Sean Carroll, uh, people like that, quantum mechanics physicists who have described in detail how the wave function works. So in this case, we are just trying to solve it by using separation of variables. Just improved, right? Substituting this into Schrodinger equation, we get this separate two different uh, solutions. Uh, on one side, you have the space component. The other side, we have the time component of the wave function. So then we can sort separately, right? Spatial part is equal to the energy times the wave function. Time dependent part equal to energy times the time component of the wave function. So separately you can solve them. And then we can solve independently each case of the potential energy, like I said mentioned. Valid solution to time depends. So It's all that I'm going to go into detail. Of course, you can work it out, and there, you can watch this video where it's worked out completely, and it has been shown that valid solution to the Schrodinger equation, which is this is the actual wave function psi of t, is a, which is a normalization parameter times time evolution, time and space. So it's an exponential solution. As we know that many of the second order equations are exponential, and you can easily prove how they became because they sinusoidal and all that, uh, and cos and sine, but essentially exponent of I, which is the imaginary variable, root of minus 1 times kx minus omega t. K in this case is the wave number times the x component, which is space, and then omega is the angular frequency times the time. So then uh, the final solution we get psi of x t, psi of x e to the minus omega t potentially is not a function of time. Okay. And these are the what are the real solutions for actually no, we cannot solve for Schrodinger equation. Only has been solved hydrogen atom. Many of the others have had to be solved by numerical methods, things like that. Although there are, I found, and one of my recent, uh, you know, uh, research or the paper article, I mentioned that actually in vacuum case you can solve it same as a fixed equation. I have proved how you can solve that as an error function. So that's a paper that I have exact solution of the Schrodinger equation vacuum based on the fixed diffusion equation because they are exactly the same if v equal to 0, same as the fixed equation, and that solution is error function complementary. Okay, now I'm going to go into details here, but in subsequent episodes we might highlight that. All right, so now let's go back to relativity. So Einstein field equation with G and Schwarzschild metric, very important. That's how the solution came into being. So Einstein field equation described the gravitational interaction in terms of curvature space. And like I mentioned before, the curvature aspect is the main thing, how the mass curves the space-time. So this is the equation, G mu nu is the Einstein equation, and this is the metric and the cosmological constant together. Uh, and then you have the stress energy tensor and the speed of light. The Schwarzschild metric uh, describes the gravitational field outside a spherically symmetric mass, just as a non-rotating black hole, and given by Ricci flat space-time, which is the Ricci tensor. Again, I'm going to go into detail about these tensors. That's a huge mathematical topic by itself. But something we may touch upon later. I'm trying to simplify these mathematical, to understand it in a simpler way. But tensor is a huge, highly complex subject. So, and you have Christopher Sigma and all that coming into picture. So in this case, Einstein himself took many years to solve the problem. Finally, he came up with because he started the uh, you know, Riemann tensor, which is a generalized form of how you can describe the geometry of curved space, right? But he found a specific solution in terms of the Ricci tensor, and so R mu nu, which is scalar as well, equal to 0. When you put that, you get magically uh, Schwarzschild could solve the problem to actually really find the solution. So G mu nu in this case is R mu nu minus half omega r. Okay, where this is called a Ricci tensor, and This is a special case, or Ricci tensor special case, or Riemann tensor. Here, the rank of the tensor is so important, right? So you have to match the rank, and if you write out the matrix, you know why you have to do that. His rank 2 tensor, that itself, mu can vary from, uh, 1 to what the space coordinates, right? All the 1, 2, 1, 2, 3, 4 for the space, and mu also can change 1, 2, 3, 4. So you have, you have to write out, uh, you know, let's say 4 by 4 matrix in this case, and that's what Schwarzschild did. This is a 4 by 4 matrix. If you write it out, the matrix form, you get a 4 by 4 matrix. And you have got interaction terms, which you can put it to 0 for this condition, and you know that way he is able to come up with this particular uh, metric. Again, I'm going to go into detail about that subsequent. Again, later episodes we may look into that, or during discussion we may look into it. So GBD combines Ricci tensor, curvature space-time on a pseudo-Riemannian manifold. So this is called pseudo-Riemannian manifold because it is a reduced rank tensor, right? That's what a Ricci tensor is, 2 by 2. So it matches, everything matches. The rank of all the all of the matches. They are all rank 2 tensors. Uh, Scalar curvature, and you have R is a scalar curvature. Okay, scalar is a tensor of rank 0, and then you give me new symmetric tensor. This is what Schwarzschild worked it out. What is symmetric tensor? It's a highly complex thing. People are trying to figure out that, but finally Schwarzschild figured out this metric tensor for this condition. This is where our black hole and L comes into picture. In this case, in this term, when 2gm over c square are equal to 1, that's you get a Schwarzschild, called the Schwarzschild radius. For example, this could describe uh, any star. So when it has Schwarzschild radius, this becomes a singularity, and that's what a black hole is. So briefly, I'm mentioning that, but it needs a lot of discussions, a lot more. You have to go through some lessons, not to really understand how that works, but quite simple way. That is what it is. But important to note is that Schwarzschild changed the type of coordinate into rotation coordinates, polar coordinates, so that he could solve the problem. Uh, so the references are profound physics. If you look into that field equation, it gives you some more flavor, some more understanding of the derivations. And of course, Wikipedia is there. It gives completed derivations of Einstein field equation, and then courses. There are many courses on relativity and also quantum mechanics. They describe the whole derivation, the mathematics of that. It's a continually evolving subject, of course. Schwarzschild himself published this. It's a German publication uh, in 1916. So Schwarzschild is the first one to solve the Einstein equation. He got Nobel Prize for that. All right. So that's briefly what it is. So I just described briefly a flavor for understanding quantum mechanics and relativity. Uh, but then, well, they solved some of the problems and they moved the physics away from classical physics, which could not solve a lot of important problems. But now it started its own problem, right? Created its own problem. So now the problem of conservation law still sticks. Only then energy conservation is still valid, and we have a problem conservation momentum we could not solve. So now we are looking into symmetry. the patterns that are very similar things. So suppose I see an object and a similar object somewhere else, I know that many of the properties are same except they are translated to each other. So I can describe them by symmetry equation. This is the idea of forming a symmetry group. But that's for lattice symmetry. Like I mentioned here, space groups. Okay, we talked about mathematics and I, being a material scientist, have done quite a lot of crystallography. Right, we have to do crystallography, crystal structures, uh, you know, crystal groups or space groups. Uh, so I have done that. Crystallographic forms like body-centered cubic, face-centered cubic, and so on, tetragonal. Uh, they all have symmetry, how the atoms are arranged in a lattice. So that's essentially what it is. So space groups are much simpler, and they describe symmetry group of repeating pattern. Essentially, like they repeat pattern, like I saw here. Patterns are repeated. You see that the same pattern, same set of patterns are repeated here. So we can, and either they are rotated or translated or tessellated or they're twisted, but we can see the basic shape is that, right? So that's how they form the symmetry group. The same way this group has its own special configuration, and so is this one. So these they remain the same, whatever transformations you do to them. They can they have some rigidity in that sense. They retain that. So that's what space groups are in three dimensions. The elements of a space group or called symmetry operations are rigid. A lot of it is rotation and you have fold, five-fold symmetry, four-fold symmetry, and so forth. So when you rotate it, the time that come back to the same pattern shows the same pattern is one of the key requirements. So they are rigid transformation, like I mentioned, that leave the pattern unchanged. Space groups are classified into 219 distinct types, or 230 types chiral copies. So when you count them, you are going to detail calculate them, you know, and then either Wikipedia or books are there to to understand them, and many courses, and we had to study them also. Uh, so chiral groups are like left-handed, right-handed, like mirror symmetries. Uh, it's three dimensions. They represent symmetry of crystals, also known as crystallographic groups. This is one of the things we have to study. Like I mentioned, face-centered or body-centered, like how the atoms are arranged in a lattice. Okay. Now, the space-time group. This is the question I have. So now we are talking about here relativity theory and even quantum mechanics eventually had to talk about the space-time groups. Like I mentioned, quantum mechanics also talk about space and time. The wave function is both function contains both space and time. As much as the relativity with the Mangossi space time in the relativity, right? In that case of relativity also we have both space and time coming together. So space-time group is very important. They describe the symmetry of space-time itself. So now we need, like I say, this is more like a Laurentian group, you can say, in general, and space-time group more like a Poincare group. These sprints include translations, rotations, and boosts, Laurentian transformations. Non-relativistic quantum mechanics, Galilean group has mass and spin existence. So if we talk about Galilean group, we include also the mass and the spin. As I say, I didn't talk a lot about the spin because that's highly, again, complex subject. But it was proved that, for example, electrons have their own spin. They rotate around their own axis as much as they rotate around the nucleus, and they have translation and things like that. So it's a highly complex subject. No question about that. In relativistic quantum mechanics, that's where the Poincare group into. uh, being come into picture. They combine space-time transformation, Lorentzian transformation, everything good. So they say, okay, how does it remain? Like I say, important thing is that the pattern has to be unchanged, right? So the Pangara group looks into how that what groups what such properties that satisfy in order to produce that. Pangara group includes both spatial and temporal. Temporal in this case, time aspect symmetries that they don't change with time, uh, reflecting the fundamental structure of space-time. So that's very important to for both quantum mechanics and relativity theory. So now we had to talk about unitary symmetry groups because now we know they can extend the lengthwise, but if the pattern is remaining the same, it's just cardinality is changing, but the eigenvalues are the same, right? So which means that we are essentially retaining the shape, the pattern, but only the size is different. So that's why you have to consider the unitary symmetry group, the scaling factor. How unitary matrices that preserve inner products. So it's called preserving the inner products. Again, what inner products are, they it's another discussion, but essentially they describe, uh, the brand ket matrices, which the ket matrices essentially describe the vector nature of that. Okay. The unitary group U of n has n unitary matrices which satisfy. So you have to satisfy certain conditions, and that is what the symmetry helps us. Okay. So all the conservation, all the symmetry, everything is that so that we can find the unknowns. Like if you know certain properties and they're moving to another place, and we know the property and we know certain parameters associated, we can figure out what is the uh, what is something that we don't know yet, right? So, like I said in later on, I described about I had come up with a general transform, talked about the whole universe is a black box. So then we have to talk about uh, what is the same, what is different between them, and that way we can figure out what the motion is, the equation of motion is, what is happening. You can describe the dynamics, the spectroscopy, uh, what elements are there, things like that. So by using these relationships, identity or the properties, we can describe uh, what's going on, like in quantum entanglement and superposition, things like that. Uh, we can figure out that. So here uh, the in this case the u times the uh, u cross, okay, or u dagger. It's also called u dagger or u cross. Um, is the conjugate transpose of u. So u is the unitary matrix, like I said, that describes the entire group, it characterizes the entire group. Again, these are highly ignored, but I'm just giving you some sampling or some flavor of what is going on here. Quantum field theory, again, it's a high level extension of these aspects, the unitary transformations that represent symmetries of physics. So we are getting into the heart of the whole physics now, using these symmetry, straight-line symmetry or HU groups, special unitary groups, things like that. They form the flux of the quantum field theory and beyond. Special unitary, that's what special unitary group, or HU, he includes unitary matrices with determinant one, right? So if you have determinant one, then we are describing almost like the eigen. And then you only need to figure out the length, how the length has changed, or the cardinality, things like that. These groups play a crucial role in understanding particle physics and quantum phenomena. So you can understand particles, how they are alike, how they are different, because all sometimes maybe they may have the same SU group. All that is changing is their size or the mass, charge, things like that. You can describe that. So the projective representation space group called GST. So they have special criteria, special things that they satisfy. And from that, we can figure out the unknowns, right? So if S naught times S1 is S2, then they have this property. Then S naught times S1 you can describe by omega that describe the property S naught S1 times the S2, right? Where Si are the symmetry elements in GST. So how they are interrelated, that's the whole idea in this case. Again, I'm just going to give you some flavor for that, but there are a lot of details that we are going to understand. Omega is called a multiplier, the projective representation. So projective representation essentially, how they how they all change the shape, how they can be, in one place with another place, how they project themselves, things like that. And then in this case, uh, there's a value that u of one, right? U of one in this case. For example, you have uh, many of the corner field theory, you can use S2 times S3 times U of 1. So that's a very simple representation of that. We'll go into detail later on, either the discussions and the further episodes. As we know that up till this episode 4, the crux of the things, essentially just basic things. But then further on, it's the complexities that we'll be examining and evolving physics because it's still research in now that we are going into from classical to quantum relativity and then to contemporary physics. Now we are going to modern physics and evolving emergent physics. We call it. So don't be surprised about how they are becoming complex. But we are trying to keep it as simple as possible, like the Occam razor principle. Uh, so up to episode 4, I think just about anybody could understand, and that's what I'm trying to do with some basic understanding. It doesn't need very advanced math or physics to understand these, I believe, but at least you'll understand what it is. But any further than that, it requires more concentrated effort, specialization, and things like that to understand them. And there are many people still trying to wrap their heads around how to put them together, right? All of us are trying to do that. Or linear and antilinear operators always satisfy the associativity. Uh, so S1, S2, S3, bracket mean they are in one group, times S3 is they have this property of associative property that you can do select. We can say one time, it's same as saying 1 times 2, and then you have outside the bracket 3, and we can put that in, use that 1, then 2 and 3 in the bracket. That's associative principle, they can associate. But you should realize that many of them have matrix properties, and the matrices does not have nice associativity like numbers. They don't have that kind of property, all the nice properties that numbers have, matrix does not have. The order matters. The order of multiplication matters in matrices, and quite simply speaking. But in this case, in this special projective representations, we are trying to get that higher properties, these properties satisfied so that we can do operations on them. So for arbitrary operation H1, H2, and H3, multiply omega satisfy equation. So, you know, so these are the omega S1, S2, S1, S3. You can see that you can do omega S1, S3 times CS1, S2, S3 can be put together, and then but you have to have an operator, uh, which is a function of the S itself, and then times omega of S2 come S3. So CS equal to 1 if S is unitary, CS equal to K if S is anti-unitary. So these properties are there, but I'm giving you a flavor for the, the whole space-time group. I'm not going to stress on the math here, just to give you what you may see in these. So the references for crystallography, you can look in international tables for crystallography, simple relation between space groups, and this is a whole series that's available, very detailed things, with all the diagrams, graphics like these, more details, more transformations and all that, translations, tessellations, different things. Uh, then Haywood is another person who worked very detailed about symmetry and the conservation. So, like I said, the conservation law is the holy grail, right? So, and the symmetry now, knowing the theorem for it, they do form the fundamentals of everything because that's how we figure out the patterns, right? Even in astrology, those are done. Like we compare, for example, two people with what symmetries they have, conservation, very similar looking, configuration of geometry, shape of the geometry, size of the geometry, and so on and so forth. How their patterns match. So this is an introduction to group theory for particle physics. So as we said, the final note, I will say that up to episode 4, you could think, most of it, in this one, if I'm 80% of it, I think you should be able to understand it. But that's a simplification I like simplified physics. And we can utilize that. We can always go back to this to refer back when you get confused or when you have doubts. And I hope that will help. Thank you very much. I hope to have discussions the coming week. And I have to end it today. Thank you very much. Talk to you. So, thank you all for today's thing, which is June 8th. I'm just putting it about a few hours earlier in this episode. Uh, and then the upcoming YouTube uh, episodes 5 to 10 will continue analyzing quantum mechanics, theory of relativity, standard model, quantum field theory, superstring theories, quantum gravity, theory of everything, and further modeling that our group is doing, advancing and solving some of the problem. For example, the vacuum catastrophe is one of the problems that really question uh, the quantum relativity and quantum mechanics and theory of relativity. They don't match. They don't correspond with each other. Why is that? So that casts big doubts on the physics itself. But we are trying to resolve that, and many people have come up with many ways to patch up that and also bring them together. Superstring theory, things like that. Uh, but later on, right now, it's quantum gravity seems to be doing somewhat better than others. But again, there are a lot of challenges, right? So thank you very much. We'll continue the exciting topic. Some of them are exotic, but they have we are coming out, the discussion will show and further down that the question of multi-universes and then, you know, many worlds interpretation, things like that is very exciting. Superpositions, quantum entanglement, and now you have quantum computing aspects which utilizes that, and then they can solve problems that present supercomputers are not able to solve, and also within fraction of time uh, as well. So these are very exciting times that we are developing, and many breakthroughs we have been able to get. And recently, I have been able to get some breakthroughs and then publishing that. And these publications going to come within in the months to come. And then very important, I want to mention about discontinuum physics I'm doing with Emery Taylor. Again, that it looks into falsification, some falsification aspects of this quantum mechanics as well as the theory of relativity, and why we have to consider something more advanced, more higher level things. That's how it came come up, right? Einstein's thing said that okay, this higher level of Newtonian mechanics. So in the reduced form, the relativity just reduces to the Newtonian mechanics, the mesoscopic level. The same with quantum mechanics is they try to do same thing, because only at super speed you have, at the close to the speed of light, you have this time dilation, things like that. Okay. But, and also the relativistic mass, only at the speed of light, you have very large, the masses increase, right? But when the speed of light, when the speed is much less, very close to zero, or much less than the speed of light, essentially, the mass remains same as the rest mass. So that's one aspect. And when I taught a course on physics for high school students, I mentioned this how the classical mechanics, and a very simple picture I can give you, that the actual quantity in this case comes from the fact that suppose that a mass is moving. Now it has created energies, right? So the energy, kinetic energy, how does it take care of the kinetic energy? Quantum mechanics says that it has to emit that heat, that energy in the form of heat. So radiation come to picture. So you have thus the wave and matter uh, combining, and that's what de Broglie came into the wavelength came into being. Uh, that considers there's both particle and wave aspects. They become important only at the quantum level. Of course, we should mention that some are particles in the mesoscopic level. If you actually measure object moving and you measure the temperature, it would have heated up because that energy is being stored, and that helps to increase the internal energy so that it becomes a little bit warmer. And we see that when we do exercise, okay, that's because our system, we warm up, our body warms up, and our temperature goes up more, right? That's true of even inorganic matter, because that energy of motion we absorb, so the total energy is increasing, right? From the rest mass, from the rest energy. So this is how the quantum mechanics looks at that. But in the case of relativity, it says that that energy is transformed into increasing the mass itself. So the mass itself increases because it absorbs that, and because of the equivalence of energy in mass in the subatomic level, the actual total mass is going to increase. Again, the mass increase may be, the mesoscopic may be very slight, right? It absorbs that. So quantum relativity looks at one way, quantum mechanics looks at one way, relativity looks at the other way. Many people say, okay, we bring them together, you have quantum relativity, aspects, then how it will look like. So then you have to develop the proper constitutive equations and figure out, right? So that's what we are trying to do. So essentially, thank you very much, and I hope that it will, promulgate inspire many discussions and debates. And we hope to do that hopefully next week or subsequent weeks, more going to more details. Thank you very much. So it took a little extra time because it involved a high level both quantum mechanics and relativity theory. So it has taken more time than other episodes. But I hope that we'll have more detailed discussions further on. Thank you very much.